right? Let's look at a situation where we have a loop with a current placed in a magnetic field, but placed in a specific way. So current I in the magnetic field, but we're looking here at a loop of a current. So the picture looks like, well, first let's see if we can understand the picture. Suppose you have a magnetic field that points into the page. So let's draw a bunch of X's. And then we will place a loop in this magnetic field. So here is the loop. I'm going to draw it like this first. I'm going to show you that I actually mean something different than what you're seeing. So here's the loop, it's just a wire. And then let's say that we send the current to flow to the left here. That implies it flows down here, flows to the right, and then flows up. Now this magnetic field, the way I drew it, field B here, points into the page, and then the current I flows to the left. Let's try to draw this in a 3D way so that I can show you that I don't really mean what I drew here. So the picture here it's a correct picture, it's what I want to show you, but it is not what you, well, look at it this way. Suppose that you have this loop drawn in, so this is 2D. Now in 3D, I would draw it like this. Here's the loop. Along some diagonal. That side, and this goes down. Comes down here. Okay. Now, going to label some points. So here's point A, here's point B, point C, and point D. So of course, here I would have A, here I would have B, here I would have C, and then here I would have D. But now what I'm going to do is I'm going to draw this. Is that what I wanted? I think so. And this comes down. To the right, and then I'm going to close this off by drawing these lines. So this is really what I'm looking at. Now the magnetic field, okay, and then of course we have the current I, so the current flows in this direction. Flows in this direction all the way around, so I have the current I. Magnetic field itself points along the x-axis. Now the x-axis, so here in the corner, I'm going to indicate my axis. This is going to be the y-axis. This one is going to be the x-axis. And this one here is going to be z-axis. That's the z-axis. So in the back corner of this little wedge, where I have my coordinate system, and the magnetic field then points along the x-axis into the YZ plane. And so I'm going to draw it like this. This point, the magnetic field points there. Here it points there. Here it points there. Along the x-axis, move out a little farther. The magnetic field points there. Here it points there. Here it points there into that plane. I'll do one more, maybe somewhere here. Actually, let's just put it. I think I would want to put, if I put it here, I think that should be good. This should be good. Then I should put one more up here. Magnetic field points into that. I'll add a few more. And here's the last one along the x-axis. And remember, this is going to be now at 90 degrees. The plane, right? This is at 90 degrees to the YZ plane. Right, so this is what I mean by this whole picture. Here's the magnetic field. So in other words, this plane here is really if I were to draw this plane here would be actually I couldn't even do that. This would be the z direction, and then this would be the y direction. So here we're looking at the plane zy. This is the zy plane. All right, now looking at this, I'm going to do one more picture. This is going to be back in 2D. So suppose that I placed you, suppose that you were right here and you were looking at this picture from this angle. There you are, let's give you an eye. There's your eye, some hair, not bad. And you're looking at it from this angle, and the picture that you would get, I'm going to draw this all the way here, would look like this. The magnetic field points to the left past your face. First, second, third, and fourth. I actually want to extend these, make these longer. And then the loop, the way you see the loop is that here's your point A. So on the top here, you would see point, this is what I want. On the top here, you would see point A. Actually, let me put it a little lower. Somewhere here, you would see point A. And then somewhere here, you would see point B. And the wire runs from this point to that point, and here's the current I. On the top, the current comes out of the page. Put a circle here with a dot. And on the bottom of the page, the current goes into the page. Put X here. All right, so now, so hopefully this makes sense. This picture here makes sense. Now let's look at the forces and how the forces act in this whole scenario. So each segment of the wire, I'm looking at this here first. Each segment of the wire is going to experience a force because I have current here in a magnetic field, I have current here in a magnetic field, I have current in a magnetic field, I have I in the magnetic field, and then there's going to be a force. Of course, the force, the equation for the force is F equals I L B sine of the angle theta. And we use the right-hand rule to determine the direction of the force. So on the top wire here, if you use the right-hand rule, you will find out that the force points down. Right, take your fingers, the fingers of your right hand, align them in the direction of the magnetic field, and so into the screen. Then the thumb has to point to the right. And in that case, the force will just point down. So you would have, well, okay. Now when you get to this side, do the same thing. By right-hand rule, you will find out that the force points in this direction. On the bottom, by the right-hand rule, you will find out that the force points up. And on this side, you will find out that the force points to the left. Right. Now, let's call the top one F1. Let's call the bottom one F2. Let's call the one on the left F3. Let's call the one here on the right F4. It's clear that F3 is equal to F4 because it's the same current, it's the same magnetic field. The two forces will have the same magnitude and they will just cancel themselves out. Right, so if you look at this picture here, the three-dimensional picture, if you look at this one, you would have here F3 pointing in this direction. Here's another F3 pointing in this direction. Then you'd have F4 pointing in opposite direction. 4 points in the opposite direction, and they just cancel themselves out. So nothing interesting happens there. All right, so let's just get rid of that. But when you look at F1 and F2, it's true that F1 will equal to F2 in magnitude, and they will point in opposite directions. But let's look at the three-dimensional picture here. The force on the top is going to point straight down, straight down. The force on the bottom is going to point straight up and straight up. And now let's give you a perspective from this picture. The point on the top is going to point, the force on the top is going to point straight down. The force on the bottom is going to point straight up. This is going to be F1, and then this is going to be F2. It's true that the two of them will be equal in magnitude, but because of the geometry, you will get this whole loop rotating. Because of F1 and F2, this whole loop will have to rotate. And if you get rotation, then you must have a torque. And this whole thing is going to rotate about the center axis here. Here's the center axis. I'm going to draw that center axis. This whole thing is going to rotate about the center axis right here, middle. So I'm going to put that right there. Maybe I'll put letter C for this center axis, I guess. And now we can go ahead and figure out the torque. So what I'm going to write here is there will be a torque. It's still true that all of these forces cancel out. In other words, F net is 0. That means that the loop as a whole, this whole loop here, will not go anywhere. It's not going to go up, it's not going to go down, it's not going to go to the right, it's not going to go to the left. It will go nowhere because of net is 0. But the net torque is not going to be 0. This thing will rotate. This thing will rotate, and so the net torque is not going to be 0. All right, so these are the concepts, and now what we need to do is find an expression for the torque. So let's find an expression for the torque on this loop. We only have to worry about the force F1 and the force F2, where F2 is the force on the bottom wire here, and F1 is the force on the top wire here. We will use this picture though to get an expression for the torque. Let's slide the screen. And so let's go ahead and first of all, let's recall the equation for the torque. So the torque equation for the torque is force times distance d times the sine of the angle alpha. Let's use alpha here. If you forgot what this means, suppose you have a lever here like that with a pivot point. So there's some kind of a pivot or axis of rotation. And then you apply a force, and let's say the force you apply points like this. Here's force F. Distance d is the distance from the axis of rotation to the point where you apply the force. So this is d. And angle theta is the angle between, or alpha here. Alpha is the angle between distance d, vector d, and force F. All right, so that was the equation for the torque. Now I have two forces here that will give me a torque, and they will give me a torque about the axis of rotation, which is, well, the axis of rotation is at the center of this thing, right? So this is the axis of rotation. Let's put, let's just put it that, write that here. This is the axis of rotation. So I have two forces, each one will contribute to the total torque. So the total torque is going to be the torque produced by F1 plus the torque produced by F2. Now let's take it a little farther. This will amount to, well, first of all, both of these torques will have the same sign. Reason being is that torque produced by F1 will generate a rotation that is counterclockwise, and torque produced by F2 will also generate the rotation that is counterclockwise. So I don't have to subtract one from the other, but I have to add them because they both will generate the same type of rotation, counterclockwise rotation. All right, so I add them. This amounts to F1 times D1 times sine alpha plus F2 times D2 times sine alpha. I guess I'll put 2 and 1 here. Okay, now D1. If this is F1, then this here is D1. Distance from the axis of rotation to where the force is applied, and then this would be alpha 1. Well, D2, if this is F2, then D2 would point from the axis of rotation to F2, and then here I would have alpha 2. From the picture, it should be pretty obvious that D1 is D2, so we will just call this D. And it should also be obvious that alpha 1 equals alpha 2, and we will just call this alpha. Further, both of the forces will have the same magnitude. F1 will equal to F2. And that comes from the fact that the equation for the force is F equals I times L times B times the sign between I and B. Now current doesn't change throughout the whole loop, so the current I is the same here as it is here. the length of the loop, remember the length that we're actually looking at is, let's bring this picture here. The length that I'm looking at is this. This is the length. The length from the top is the same as the length from the length of this wire on the bottom. The two L's are the same. So this L is the same as that L. So bringing this thing back here, I is the same on the top as on the bottom. L is the same on the top as on the bottom, and B is constant everywhere. The angle between B and I is also the same on top as on the bottom. So let's see if we can make sense out of that. What is the angle between I and B? On the top, the magnetic field points to the left and the current comes out of the page. Therefore, the angle theta, which is the angle between B and I, is 90 degrees. On the bottom, the current points into the page and the magnetic field points to the left. Therefore, the angle theta, angle between I and B, is also 90 degrees. So theta is the same for both F1 and F2. All right, so now what I can do is I can rewrite the total torque as 2 times F times D times the sine of alpha. Now 2D is just the length. Let's bring the screen back to the left here. Oh, I see. Well, we're going to assume that this length here is also just L. So we have a square loop. This thing here is L. And in that sense, and of course the other side here, this would also be L. If this is L, then this is also L. So I have a square loop. And so 2 times D, this distance here, 2 times D, that's just going to give me L, right? So if I draw this out like this, this is nothing but simply L. And so the total torque is going to be F times L times the sine of the angle alpha. Now let's bring the screen back here. Let's substitute an expression for the force, magnetic force, on the current, and that would just be I times L times B times sine of 90. We already figured this out. This is 90 times. So all of this, by the way, just in case you're wondering what just happened, all of this here, all of this here, that's just force F, comes from here. And theta was 90, so I'm going to put here, theta was 90. It's the angle between B and I. Times L times, oh, let's change the color. So times L times the sine of alpha. We still have to figure out this alpha piece. But anyways, so now what I have here is sine of 90 is just 1. So the total torque is going to be I times L squared times B times the sine of alpha. Now L squared is the area of the loop. And so this is the final expression now. I times A times B times the sine of alpha. This would be the expression for the magnitude of the torque, where A is the area of the loop. Area of the loop. And you can calculate A if you know the side of it is just L squared. Now you might notice that this can be turned into a vector, which it should be because torque is a vector. And that would amount to I times A cross B. Since A cross B is A times B times the sine of the angle alpha, where alpha is the angle between A and B. Now this expression here, that's really for the calculus-based physics class. In algebra-based physics class, we won't really need it. So if you're in algebra-based physics class, you're responsible for this equation. If you're in calculus-based physics class, you're responsible for both of these equations. so now we will go on a tangent a bit. That will be useful, and that is, well, we have to still figure out, we have to do something with this alpha here. This is the angle between A and B, but we have to figure out how to turn area A into a vector. And so I'm going to circle that, and I'm going to circle this, and let's go on a tangent that will demystify some of it. So let's slide the screen to the left, and let's see how an area can be a vector. So area as a vector. All right, so suppose you have a cube. So here's a cube. Each side has an area, but each side points in a different direction. So you could indicate that by doing the following. Here's vector A, where the magnitude of this vector is the actual size of this area, and then that points in a direction that is perpendicular to the, well, points in this direction. Now on the side here, you will have also a vector, where the magnitude of this a vector is, well, the size of the area of the side, but this vector also points in a certain specific direction, 90 degrees. I'll do one more. In the front here, you have vector A, which the magnitude of this vector A is the actual size of this area here. And this thing points at 90 degrees to the surface. So why would you want that? Why would you want to turn area into a vector? Well, suppose that you have a surface that is curved that looks like this. And then maybe it just does something like that. Right, so this is it. Try to picture this in 3D, some kind of a sheet that bends like this. Well, you could indicate the curvature. You could actually specify how much this thing curves at every single point in space by putting these A vectors all over the place. So here A points like that, but here maybe A points like this. Somewhere here A might point like this. Somewhere at this point A might point like that, and then here maybe it points like this, and then here it points like that. So 90, 90, 90 to the surface, 90 to the surface, 90 to the surface, and 90 to the surface. So the vector A, they indicate how the surface curves. So it's useful to turn area into a vector. It's very useful actually to do that. Now in the case of our loop, so we have is a loop that looks like this. Let's see if we can give it some depth. So here's this wedge. This is the loop that we have. And then the current flows to the left like this, and then goes down, and it goes to the right, and it goes back up. A vector would be perpendicular to the surface. And so somewhere here at the center, you don't have to put it at the center, but it's typical to put it at the center. You would draw a vector that points up like this. And it is at 90 degrees. Let's see if I can draw this at 90 degrees to the surface itself. This would be a vector. Now, if you were to look at it from, so this is in 3D. If you were to look at it from the side, then you would have, right, so this, your face is here, your nose, mouth, give you an eye, some hair. You're looking at it from this direction here, you would see that the current is coming out of the page towards you and goes at an angle like that, and then goes into the page. So X on the bottom. And in that case, so let's maybe add points to this. So here's point A, and this is my point A. Here's point B. This is my point B here. The area vector would point like this. A vector, 90 degrees to the surface of the loop. Whether your A vector points in this direction or whether it points in this direction is irrelevant. You could have drawn it like this. You could have drawn this thing like that, that this is the A vector and it's at 90 degrees here. That would have been perfectly fine. That's not an issue. That's not a problem. You choose which way you want it to point. In some problems, it may be easier to have the A vector point in a specific direction. But anyways, let's just stick with And actually, let's do that. Let's use this as the a vector. So this is the a vector here, always perpendicular to the surface. And now let's go back to our equations. So let's see if we can put A in our picture. Well, at the midpoint here, I'm going to draw a vector that is pointing like this at the angle that is 90 degrees to that surface. This is the a vector. And here's another interesting piece. I'm going to leave this to you as an exercise. So angle theta, let's use a different color now, maybe something like red. This angle theta here, which is the angle between, I'm going to put here theta, this is the angle between vector A and vector B. Which is also this, right? That's alpha, this is alpha. But as it turns out, it is also this, it's the same thing as this. All these angles, this one, so this one, and this one, they're all the same angle. And I'll leave that to you to confirm that that is the case, but that's that. So in general, let me now sort of review this whole thing. If you have a current I that loops around in a circle, well, not really in a circle, loops around like this, where each side has length L. So this is L, this is L, this is L, and then this is L. And this thing is placed in a magnetic field. So let's give it some depth here as well. So we have, that's 90 degrees. There's a wedge here. And then we have a magnetic field, and the magnetic field points, well, it points that way. Points like that. This is the magnetic field B here. The here's a vector, by the way. So at the center here, this thing points out like that, and it's at 90 degrees to the surface. This is a vector. You can calculate the torque produced by this setup by writing out the following: I times A times B times the sine of the angle alpha, where the angle alpha is the angle between A and B. In some problems, it may be easier to see what this angle is than in other problems. A is the area, B is the magnetic field, I is the current. So this must be in meters squared, this must be in amps. B is the magnetic field. I'll just write this as magnetic field here. Units are Teslas. And the vector equation of this is I A cross B. For 1201 class, this is the equation you will be responsible for the 1402. Both of these equations is what you're responsible for. Okay.